Welcome to my ASRU 2023 presentation. I'm Wang Yu from Shanghai Jiaotong University. This is the joint work of Shanghai Jiaotong University and Samsung Research China. Here, I will introduce our paper exploring time-frequency domain target speaker extraction for causal and non-causal processing. First, let me introduce the task definition of target speaker extraction, or TSE for short. It aims to extract or separate the voice of the target speaker from a mixture signal that contains sound from different sources such as interference speakers or background noise. In most TSE approaches, the extraction is achieved by utilizing an additional input, which can be an individual enrollment audio spoken by the target speaker or a speaker embedding extracted by an external model that corresponds to the target speaker. Generally speaking, a TSE model is usually composed of three components: the encoder, the extractor, and the decoder. If the encoder and decoder are based on SDFT and ISDFT respectively, the corresponding TSE approach is often called the time-frequency domain approach. If they are learnable conv1D layers, then the corresponding TSE approach is often called the time domain approach. Nowadays, it can be observed that the state-of-the-art TSE models are basically time domain approaches, using learnable conv1D layers as encoder or decoder, and with different backbones. For example, the time domain speaker bin and SPEX series models use the TCN as a backbone. X subformer use dual-path transformer as the backbone, and the VVN use dual-path RNN as the backbone. More recently, time-frequency domain approaches have achieved superior performance in speech separation, outperforming many time domain approaches. And many existing approaches adopt complex loss functions or training procedures, making it less flexible to extend to large-scale data. In addition, most approaches only focus on non-causal TSE, while causal TSE is less improved in recent years. So in this paper, we revisit the time-frequency domain approach for TSE, which has lagged behind time domain TSE approaches for a long time. And we will show that our proposed time-frequency domain dual-path model can achieve a new state-of-the-art performance on various benchmarks with a very simple loss function and training procedure. We also explore two different fusion approaches to incorporate the target speaker information into the proposed model. And finally, we demonstrate that the proposed model can be easily extended to a causal setting with sort of performance as well. So the architecture of the proposed time-frequency domain TSE model is shown in this figure. Different from previous TSE models, we devise a pooling module with two variants to extract the speaker representation from the provided enrollment audio. So now I will introduce each component in the model. The encoder and decoder are basically composed of SDFT and ISDFT. However, we additionally project each time frequency bin in the SDFT spectrum into an embedding, and which will be used for later processing. Similarly, the decoder maps the embedding back to the SDFT spectrum, and finally the waveform. Note that the encoder module is shared between the mixture signal processing and the enrollment audio encoding. The pooling module takes the SDFT representation as the input and generates a fixed size speaker representation, which will be utilized later in the extraction module. Here we explored two ways to extract the speaker representation. In the V1 approach, we simply average the representation along the time dimension, which results in an F by D feature. In the V2 approach, we take inspiration from the Percival I/O approach and design a set of learnable tokens to convert the variable length input representation into a fixed length output via cross-attention. Here, G is the number of learnable tokens. Next, the extraction module is the key component to achieve target speaker extraction. It is mainly composed of dual-pass transformer blocks, which utilizes improved transformer layers to conduct sequence modeling along the frequency and time dimension respectively. To leverage the two kinds of speaker representations provided by pooling module, we designed two different fusion approaches in the extraction module. For the V1 approach, we concatenate the speaker representation frame-wisely to the input feature before each dual-pass block, like shown in the V1 figure. For the V2 approach, we concatenate the speaker representation to the SDFT representation along the time dimension, resulting in a longer feature sequence. The transformer layers in the dual-pass blocks will implicitly utilize this concatenated longer sequence and with the attention mechanism. While the proposed model is by default a non-causal model due to the use of global attention in the transformer layers, it can be easily extended for causal processing by replacing the global attention in all time dimension transformers with causal attention. In our implementation, the causal attention mechanism is achieved by limiting the attention span only to the current and past frames, while the look-back size is fixed at all time steps. We conducted experiments on two speech separation benchmarks. The first is WSJ02 mix, which contains the clean mixture of two different speakers. We follow the previous work to adopt a predefined enrollment list for each test sample so that our results can be comparable to other reported numbers. We first compare the performance with the existing SOTA time domain approaches in the non-causal setting. We can see that both proposed speaker information fusion approaches, V1 and V2, can achieve very competitive performance, and they have outperformed the previous time domain TSE approaches by a large margin. It is worth noting that our proposed model only adopts a single SISNR loss function for training, while many time domain approaches listed above adopt a complicated training procedure, either involving multi-stage training or using multi-task training with additional labels. In the literature, the causal TSE performance are less mentioned. Here, we aim to fill this gap by evaluating the proposed model in the causal setting. It can be seen that even though the performance becomes worse compared to the best performance in the non-causal setting, it still outperforms the existing causal approach in the literature, and even surpasses some non-causal approaches listed above. This shows that our proposed approach is promising for both causal and non-causal processing. We also evaluate the proposed approach on another popular benchmark, that is LibriMix. Note that we adopted the noisy version of LibriMix data, which makes the task more difficult. And from the table, we can see that the proposed model consistently outperforms the previous time domain approaches and can be improved when more training data are available. To summarize, we have proposed a time frequency domain TSE model that achieves SOTA performance in various benchmarks, which not only surpass existing time domain approaches, but also enjoy a simple loss function and training procedure. We proposed two speaker information fusion methods in the proposed model, both of which are proven effective. And we also show that the proposed model can be easily extended for causal processing with SOTA performance. Thank you for listening. If you have any questions, feel free to contact me via email.